Continuing now with question number 7, we're going to be dealing with the scenario of cards that are drawn and we are putting them back after we draw them. This is called with replacement. So you randomly draw 2 cards with replacement means that after you have shuffled together these cards and you've drawn the first one, then you're going to put that card back, shuffle again, and then draw the second one. So because of the issue of replacement, we can say that the individual draws of the card are going to be independent events. Drawing one will not impact drawing the next one because you've put the first one back. So the probability of G1 and G2, probability of at least one green, and the probability of green on the second draw given green on the first draw, and our green on the first draw and green on the second draw independent are all questions that we would like to go over, and I'm going to do them in a specific order, starting with D, and then A, and then C, and lastly we'll do B. So with regards to D, are G1 and G2 independent? Yes, because you're putting the cards back after you draw them. So for G1 and G2 to both happen, you draw the first card green, you draw the second card green. Because we have independence, we can simply multiply the 2 individual probabilities together, 8 over 13 times 8 over 13, and get 0.3787. So next we're going to look at C, the probability of drawing the green on the second turn, given that we've drawn green on the first turn. Well, remember that if we're taking that first card that we drew and putting it back into the deck, then there is going to be no impact on that second draw. In other words, when you have independent events, the probability of A given B is simply the probability of A. So that means that this probability for C is simply going to be the same as if we're looking at the probability of green 2 by itself. And that's 8 over 13. Okay, so now for the harder question, the probability of at least one green. I'm going to show you this 2 different ways. First way, in what cases do we have at least one green? Well, you could have the first draw green, but not the second. You could have the second draw green, but not the first. Or you could have the first and second draw both green. Since these 3 scenarios are mutually exclusive, we can apply the addition rule and say that the probability of at least one green is the probability of green first draw but not second draw, plus the probability of green second draw but not first draw, plus the probability of both draws being green. We add each of these up and we get 0.8521. Where is the 5 out of 13 coming from? Well, if we have 8 green cards and 5 yellow cards for a total of 13 cards, that's how we get the denominator. Anytime you see an 8, that's representing drawing a green card. A second card not green means that it's yellow, hence 5 over 13. Now this is the more complicated way of doing this problem, so now let me show you a shorter way. Another way to express at least one green is to say that this scenario is the complement of both cards are yellow. So because the probability of at least one green, which covers 3 different scenarios, plus the probability of both cards yellow, encompass all possible outcomes of drawing the cards, the sum of these 2 is going to be 1. This is 100% of the time you're either going to get both cards are yellow, or you're going to get at least one green card. So if we rearrange this equation, we could say that the probability of at least one green is equal to 1 minus the probability of both cards yellow. Remember, this is called the complement. So what is the probability that both cards are yellow? That would be 5 over 13 times 5 over 13, since they are independent events. And you can see we get the same answer, but a lot faster than the previous way. So here's all of our answers together. And now moving on to the next question. First, let me just point out that there are plenty of scenarios where you are looking at events that are neither independent nor mutually exclusive. For probability problems that involve events which are neither independent nor mutually exclusive, such as drawing marbles without replacement, you still use the multiplication rule, but it involves conditional probability. And you could write it either way. So, number 13. May buys a bag of cookies that contains 7 chocolate chip cookies, 8 peanut butter cookies, 7 sugar cookies, and 5 oatmeal cookies. What is the probability that May reaches in the bag and randomly selects 2 peanut butter cookies from the bag? Now notice that May is not putting the first peanut butter cookie back and then drawing a second cookie. May draws 1 peanut butter cookie, keeps it, and then draws a second cookie. So we're going to look at this scenario because it involves conditional probability. The formula that we would want to use is A and B is P of A times PB given A. So A is going to be the first cookie is a peanut butter cookie. B, the second cookie is a peanut butter cookie. So the probability of A and B is going to be the probability of A. There are 8 peanut butter cookies out of a total of 27 cookies. Then we have the tricky scenario of figuring out the probability of B given A, which I'm going to elaborate on momentarily. But once you find that, you simply multiply these two values together, and you end up with this 7.98%. And that would be the probability of drawing both the cookies. So now let me explain how I'm getting the 7 over 26. Here are all the cookies. There are 7 chocolate chip cookies, 8 peanut butter cookies, 7 sugar cookies, and 5 oatmeal cookies. So if you draw the first peanut butter cookie, of course you have a probability of 8 out of the total of 27. But let's say we draw one of these peanut butter cookies out of here. That one. Okay? So we're taking it out. And now, look, there's only 26 cookies left. And notice also that the peanut butter cookies that we're looking at, there are only 7 of them left. That's how we're getting the 7 over 26. So with only 26 cookies left, because there are only 7 peanut butter cookies left, the probability of drawing a peanut butter cookie for the second cookie is 7 over 26. Question 15. I know this is a lot of parts and it can be a little overwhelming looking at all of these at once, and so I'm going to break it up. But let's just look at the scenario. First of all, we've got peanut butter M&Ms. And in the vast population of millions or billions of M&Ms out there, 12% of those peanut butter M&Ms are brown, 15% are yellow, 12% are red, 23% are blue, 23% are orange, and 15% are green. So we're going to use these percentages to figure out each of these 5 individual problems. So let's first look at A and B. Compute the probability that a randomly selected peanut M&M is not orange. So we would write probability of not orange, and that would be the complement of probability of orange. So 1 minus the probability of orange is all the scenarios where you have not orange. Since 23% of them are orange, 1 minus 23% is 77%. Part B. Compute the probability that a randomly selected peanut M&M is green or brown. So remember, when you are selecting just one M&M, green and brown are mutually exclusive because you cannot draw a green and a brown M&M at the same time if you only draw one M&M. So probability of green or brown is simply the probability of green plus the probability of brown, and that would then be 0.15 plus 0.12, corresponding to, up here, we've got the 15% green and 12% brown. Add those together, and you've got 27%. Next scenario. Compute the probability that 2 randomly selected peanut M&Ms are both orange. Now, just like the dog problem, where you're drawing a human out of a huge population, it really doesn't matter whether you replace that first human or not, because there are just too many people to choose from, and if your whole population is randomly selecting a person. And if you're looking at millions or billions of M&Ms, whether you put back that first M&M or not is not going to make a difference for your probability computation. So we can assume then that this is going to function as independent events, that drawing the first M&M orange is not going to impact the millions or billions of M&Ms left. So the probability of orange and orange, we would say then, are independent events, and that would be the probability of orange times the probability of orange, 0.23 times 0.23, or 5.3%. D and E. If you randomly select 5 peanut M&Ms, compute the probability that none of them are brown. So, in this case, this is a lot more complicated, but the probability of none of them being brown, another way of saying that is that all 5 of them are not brown, is you're going to take a single instance of it not being brown, so 1 minus probability of brown would be the probability of it not being brown, and raise it to the 5th power, because each of these 5 are getting multiplied together. They are independent events. Each one of these 5 peanut M&Ms that you draw are independent draws of each other. So instead of multiplying this value of 0.88 times 0.88 times 0.88 times 0.88 times, etc., you just raise it to the 5th power, and that's how we're getting the 0.528. If you randomly select 5 peanut M&Ms, compute the probability that at least one of them is brown. Well, look at what we looked at. Look at part D. Part D is the probability that none of them are brown. So at least one of them being brown and the probability of none of them being brown have to add up to 100%. One of these two scenarios is going to happen. So this is simply going to be the complement of part D. At least one brown is 1 minus probability of none brown. So that means you've got a 47.2%. Okay, question 17 is very similar to question 7, except now I did change the numbers here. We have 7 green cards and 5 yellow cards. And then the second situation we're looking at is that this is without replacement. So after we draw the first card, we're going to keep it. So part D, in this case, are G1 and G2 independent? No. Once you draw your first card, it will impact the probability of the second card. So the probability of drawing a green card on the second card, given that the first card has already been drawn, and that the first card was already green, like the cookie situation, after you draw a first card, there are only 11 left. And of those 11 cards that are left, only 6 of them now are green because the first one already got pulled out. These two are independent events. Hold on. Sorry about that. Let me fix that real quick. I said something incorrect. These two are not independent. Originally, I had written probability of green 2 here, and I've just corrected it. But what we're looking at, because we have two that are not independent, is that the first probability is fine as probability of green 1, but when we get to the second one, we have to use a conditional probability for the multiplication rule. So this is the probability of green 2 given green 1, which we've already computed down here, and that's how we get the correct answer. And then at least one green, again we can use the complement. So in this case, 1 minus the probability that both cards are yellow would be 1 minus 5 over 12 times 4 over 11. Again, the first card being yellow would be 5 out of 12 because we start with 5 yellow cards and 12 total cards. Once that first yellow card has been drawn, we now only have 4 yellow cards left of the 11 cards remaining. So we're going to multiply these two together and then subtract from 1, and we get 0.8485. Okay, tree diagrams we will continue in the next video.